There is a number that sounds small, trivial even. 1 light year. We hear it constantly in documentaries and science articles, in casual conversations about space. The nearest star is just over 4 light years away. Andromeda is 2.5 million light years. The observable universe is 93 billion. The number gets thrown around so easily that we have stopped noticing what it actually means. Tonight, we are going to fix that. Because the truth is that 1 light year, just one, is a distance so vast, so utterly inhuman in its scale, that no machine humanity has ever built, no propulsion system we have ever designed, no realistic technology we have on any drawing board could cross it inside a single human lifetime. And the deeper you look into what it would actually take to cover that distance, the more terrifying the number becomes, not because of what is out there, but because of what is in between. The emptiness, the cold, the radiation, the clock, the math, the fact that the universe is built on a scale where our fastest ambitions look like a man trying to walk across an ocean. If you enjoy our nighttime science journeys here at Hidden Beyond Stars, please take a moment to leave a like and subscribe to the channel. It genuinely helps us continue producing these long, deep explorations into the cosmos. And in the comments below, tell us what you think the first interstellar mission will actually look like. Will it be a probe, a swarm, a frozen crew, or will we ever go at all? Now let us begin. Let us start with the unit itself. A light year is the distance light travels through a vacuum in 1 Earth year. Light is the fastest thing the universe permits. Nothing made of matter can ever quite reach its speed. Nothing carrying information can ever exceed it. It is the absolute ceiling on the velocity of cause and effect itself. And in 1 year of unbroken travel, light covers approximately 9.46 trillion kilometers, just under 5.88 trillion miles. Write that number out and stare at it. 460 billion kilometers. 9.5 trillion. The human brain did not evolve to feel a number like that. It evolved to estimate distances measured in paces and bowshots. A few hundred meters at most. A few kilometers in extreme cases. When you tell a person that the nearest grocery store is 12 kilometers away, they have a felt sense of what that means. When you tell them that 1 light year is 9.46 trillion kilometers, they hear a word that means a lot. They do not hear the weight of it. They cannot. The brain simply refuses. So let us bring it down a level. Let us turn it into something the body can almost imagine. Imagine that you are flying in a commercial airliner at cruising altitude, roughly 900 kilometers per hour. The plane is over the ocean. There is nothing below you but water. You sit in your seat. The cabin hums. The hours pass. You fly for 1 full year without ever landing. You burn fuel that does not exist. You eat food that cannot be carried. You ignore biology. You ignore physics. You just fly. And at the end of that year of continuous airline travel, you have covered roughly 7.9 million kilometers. That sounds enormous. A light year is 9.46 trillion. To cover 1 light year at airline speed, you would need to fly continuously without stopping for approximately 1.2 million years. Not a century. Not 1,000 years. More than 1 million. 1 million years ago, our ancestors were Homo erectus. They were just learning to consistently use fire. They had not yet developed agriculture, language as we know it, written communication, or any of the things we consider central to being human. If one of them had stepped onto an aircraft 1 million years ago, and the aircraft had simply continued flying at cruising speed since that moment, it would still not have completed a single light year. It would not even be close. It would still have decades of additional flight ahead of it. That is 1 light year at the speed of a commercial jet. But of course, no airliner could ever sustain that. Aircraft are designed for the lower atmosphere of Earth. They cannot operate in vacuum. They cannot accelerate to escape velocity. They cannot leave the planet. So we have to look at the things that actually do leave the planet. Right now, the fastest object ever built by human hands is the Parker Solar Probe. Launched by NASA in 2018, it is a small spacecraft about the size of a car designed to study the outer atmosphere of the Sun. To do its work, it must fly extraordinarily close to our star, closer than any spacecraft has ever flown. And to survive there, it has to be moving extremely fast. During its closest approaches, when the sun's gravity pulls it through perihelion, the Parker Solar Probe reaches speeds of approximately 700,000 kilometers per hour. That works out to roughly 192 kilometers every second. Every single second. The fastest thing humans have ever made. At that speed, the Parker Solar Probe could cross the entire continental United States in about 20 seconds. It could cross the Pacific Ocean from Los Angeles to Tokyo in less than a minute. It could fly from the Earth to the Moon in about 30 minutes. It is fast in a way that human imagination cannot really hold. And at that speed, the absolute fastest object we have ever built, crossing 1 light-year, would take approximately 540 years. 1,540 years. Imagine the Roman Empire at its height. Imagine a craftsman in a workshop in Rome around the time of Emperor Marcus Aurelius, launching a vehicle at the Parker Solar Probe's peak velocity and aiming it at a fixed point 1 light-year away. That craftsman would die. His children would die. His grandchildren. His entire civilization would rise and fall. The Roman Empire would collapse. The Byzantine Empire would rise and fall. The Islamic Golden Age would come and go. The Vikings would raid and settle and disappear. The Mongol Empire would sweep across Asia and dissolve. The Renaissance would bloom in Italy. The Black Death would kill 1/3 of Europe. Christopher Columbus would sail to the Americas. The Enlightenment would arrive. The Industrial Revolution would transform the planet. The American and French revolutions would reshape political order. Napoleon would rise and fall. 2 world wars would consume the 20th century. The atomic age would begin. The space age would begin. Humans would walk on the moon. The internet would be invented. Every grandparent and great-grandparent you have ever heard of would have lived and died many times over. And only now, today, in the present moment, would the vehicle finally complete its journey. 1 light-year covered by the fastest thing we know how to make. And the Parker Solar Probe only reaches those speeds in a brief swoop near the sun. It is not maintaining 700,000 kilometers per hour. Outside its close passes, it is much slower. The average velocity of any realistic interstellar trajectory is far below the Parker peak. And the moment we start thinking about a craft that is not just falling toward a star but actually trying to depart the solar system in a sustained outbound direction, the numbers collapse dramatically. This is where Voyager 1 comes in. Voyager 1 launched in 1977. It was one of 2 spacecraft sent by NASA to perform a grand tour of the outer planets. Its mission was to fly by Jupiter and Saturn and use their gravity to slingshot itself out of the solar system entirely. It succeeded. After photographing Jupiter, Saturn, and the rings and moons of both giants, Voyager 1 began the longest one-way journey any human-made object has ever undertaken. It is still traveling. It is still transmitting, faintly, on power so low that engineers on the ground have been gradually turning off its instruments to conserve electricity. The signal it sends back now is so weak that by the time it reaches Earth it carries less power than the light of a single distant star. Voyager 1 is currently moving at approximately 17 kilometers per second relative to the Sun. That is about 61,000 kilometers per hour. By any human measure, this is staggering. Faster than any rifle bullet. Faster than the rotational speed of the Earth at its equator. Faster than the orbital speed of the International Space Station. And yet, on the scale of 1 light-year, this velocity is almost laughable. At Voyager 1's speed, crossing a single light-year would take approximately 17,700 years. 17,700 years. To put that in context, the entire span of recorded human history, from the first cuneiform tablets in ancient Sumer to this moment, covers only about 500 years. The journey Voyager would have to make to cross 1 light-year is more than 3 times longer than the entirety of written civilization. If Voyager 1 had been launched at the time the last ice age ended, when the great glacial sheets were retreating across North America and Eurasia, when the first humans were beginning to experiment with planting wild grains, when the first villages were being established in what would become Turkey and the Levant, when Göbekli Tepe was being built on a hilltop in Anatolia, when woolly mammoths still walked the steppe, Voyager 1 launched at that moment, traveling at its current speed, would only now in 2026 have covered roughly 6/10 of a single light. It would still have 8,000 years of additional travel ahead of it before it crossed the 1 light-year mark. And remember, this is the fastest object that humanity has actually launched on a trajectory away from the solar system. Not a theoretical concept, not a thought experiment. Voyager 1 is real. It is out there right now. It is doing exactly this. And it is moving so slowly relative to the distance it would need to cover that the journey is functionally impossible on any timescale relevant to a biological civilization. Now consider that 1 light-year is not even the distance to the nearest star. Proxima Centauri, the closest stellar neighbor to our Sun, sits at approximately 4.24 light-years away. That is more than 4 times the distance we have just been discussing. At Voyager 1's velocity, reaching Proxima Centauri would require approximately 75,000 years. That number is so large that human civilization could rise, fall, and rise again multiple times during the transit and still not be there. And Proxima Centauri is our closest neighbor. There is no star closer, there is no shorter trip available within our galactic neighborhood. So 1 light-year is not just a unit of cosmic distance. It is a barrier. A wall built from kilometers, from physics, from the simple unyielding arithmetic of how far light travels in a year compared to how fast anything we have ever built can move. It is a moat surrounding every star in the galaxy. And to cross it requires not just a faster spacecraft. It requires a fundamentally different relationship with energy, with time, and with the nature of the human body itself. Because here is the part that almost no one talks about. Going faster is not just hard. Going faster is, on a physical level, increasingly impossible the closer you try to approach the speeds that would make interstellar travel meaningful. In classical Newtonian physics, the world of bullets and cars and even rockets we tend to imagine, doubling your speed just means doubling the amount of energy you need. You burn more fuel, you go faster. The relationship is roughly linear in an everyday sense, mediated by the kinetic energy equation. But that equation only works at speeds much slower than the speed of light. Once you start approaching the speed of light, Einstein's special relativity takes over, and the rules change in a way that makes interstellar travel almost grotesquely demanding. According to relativity, as an object with mass approaches the speed of light, its effective mass, as measured by the energy required to accelerate it further, increases. Not slightly, dramatically. At 10% the speed of light, the effect is small but measurable. At 50%, it is significant. At 90%, it is staggering. At 99%, you would need almost 7 times more energy to accelerate a given mass than its rest energy would suggest. At 99.99%, the energy requirements skyrocket into regions that defy comprehension. As you approach the speed of light, the energy required to accelerate even a single gram of matter further becomes infinite. The universe will not let you reach the speed of light. It is a mathematical wall. And we are not talking about a single gram. We are talking about a spacecraft. A spacecraft heavy enough to carry instruments, shielding, fuel, structural integrity, and possibly human passengers. All the equipment needed to keep them alive for the duration of the trip. So let us imagine, just for a moment, that we could somehow build a spacecraft capable of accelerating to 10% the speed of light. 10%. That is the speed proposed by serious research programs like Breakthrough Starshot, which has explored the possibility of sending tiny gram-scale probes to nearby stars using powerful laser arrays to push them. At 10% the speed of light, a spacecraft could cross 1 light-year in approximately 10 years. That sounds reasonable, that sounds almost human, but to reach 10% the speed of light, you would need to accelerate the spacecraft to roughly 30,000 kilometers per second. The Parker Solar Probe at its absolute fastest moves at 192 kilometers per second. So you would need to accelerate something to more than 150 times the speed of the fastest object humanity has ever made. And you would need to do it while still carrying enough fuel or propellant or photon-reflective material to actually receive and use the acceleration. The energy required for a probe of meaningful size to reach this velocity is comparable to a significant fraction of the entire annual electricity output of the United States, focused into a single laser array, sustained for years. And that is just to reach the speed. You also need to slow down at the other end if you want to do anything useful when you arrive. Slowing down doubles the fuel requirement. Or you have to find some way to brake against the destination star's radiation pressure or magnetic field, neither of which is a mature technology. But let us pretend, generously, that we have solved all those problems. We have built our craft. We have accelerated it to 10% the speed of light. We are ready to cross 1 light year. Now we run into another wall. A wall made of nothing. Empty space is not really empty. Even in the regions between stars, where the matter density drops by orders of magnitude compared to Earth's atmosphere, there is still gas. There is still dust. There are still individual atoms drifting through the dark, mostly hydrogen, occasionally helium, occasionally a stray heavier particle, all left over from the births and deaths of stars over billions of years. On a human scale, these atoms are so sparse that you would never notice them. You could fly a regular airplane through this void for a year and not encounter enough particles to fill a thimble. But when you are moving at 10% the speed of light, the physics changes completely. At those velocities, every single hydrogen atom in your path becomes a high-energy projectile. It does not push gently against your spacecraft. It slams into it with the energy of a particle accelerator. Each individual proton in the interstellar medium effectively becomes a tiny piece of radiation. Multiply that by trillions upon trillions of atoms across a 1 light-year journey, and you are bathing your spacecraft in continuous high-energy bombardment. Any forward-facing surface would be eroded. Any electronics would be steadily degraded. Any biological tissue would be cooked from the inside out by ionizing radiation. The hull would need to be wrapped in shielding so massive that it might dwarf the entire rest of the spacecraft. And that shielding would itself be slowly ground down by the impacts. And these are just the individual atoms. The interstellar medium also contains dust grains. Most are smaller than a micron, some are larger. At 10% the speed of light, even a microscopic grain of silicate dust carries the kinetic energy of a small bomb. A grain just 1 millimeter across, the size of a grain of sand, would deliver a strike with energy comparable to several tons of TNT. There are not many of these in interstellar space, but there are some. And over a trillion-kilometer journey, your probability of encountering one approaches certainty. A single hit on the wrong place at relativistic speeds would not damage your spacecraft. It would vaporize it. There would be nothing left to identify. The fragments would themselves become high-velocity shrapnel scattering across the void. This is not science fiction. This is not speculation. This is the engineering reality that any real interstellar mission would have to confront. To cross even 1 light-year at any speed approaching what would make the journey practical in human timescales, you have to solve the problem of being inside what is effectively a continuous cosmic firing range. Every cubic centimeter of space in front of you is a potential threat. Every kilometer is a potential disaster. This is why proposals like Breakthrough Starshot focused on probes the size of postage stamps. Not because we lack the ambition to send something larger, but because the smaller and lighter the spacecraft, the less energy is required to accelerate it, and the smaller the cross-section it presents to the lethal sleet of interstellar matter. A gram-scale probe might survive. A car-sized probe almost certainly would not. A human-occupied vessel is essentially out of the question for any near-term technology, and we have not even talked about time yet. The faster you move, the more strangely time behaves. Special relativity tells us that the closer you approach the speed of light, the slower time passes for you relative to a stationary observer. This is called time dilation, and it is not a theoretical curiosity. It has been measured. It has been confirmed by atomic clocks on aircraft and on the International Space Station. Time genuinely does run slower for fast-moving objects, and the effect becomes severe near the speed of light. For a spacecraft traveling at 10% the speed of light, time dilation is small, but not zero. The crew would experience about 0.5% less time than people on Earth. Over a 10-year journey, that would amount to roughly 18 days of difference. Noticeable, but not dramatic. But at higher speeds, the effect grows fast. At 50% the speed of light, the gap widens significantly. At 90%, time on the spacecraft passes at less than half the rate it does on Earth. At 99%, it slows to about 1/7. At 99.99%, the crew would experience only 1/70th of the time their families on Earth would experience. A journey that takes a single subjective year for the travelers might mean that 70 years pass on Earth. Everyone they knew would be old. Many would be dead. The civilization they left behind would have changed beyond recognition. Children would have grown up, had children of their own, and grown old themselves. The crew would step off the spacecraft into a world that had moved on without them. This is the relativistic bargain. You can, in principle, cross great distances in subjective time that does not exceed a human lifetime. But the price is that you can never go back. The Earth that exists when you arrive at your destination is not the Earth you left, and the Earth that exists when you return, if you ever did, would be even further removed. Friends, family, the political and cultural world you knew, all of it would be archaeological by the time you came home. You would be a survivor in the strictest sense, the last of your kind. And that is, at speeds we cannot currently achieve. At the speeds we can actually reach, time dilation is not the gift. Time dilation is irrelevant. The journey simply takes too long, by the regular earthbound clock, for any biological human to ever complete it. A Voyager-style craft crossing 1 light-year takes 17,700 years. No one is awake for that. No one is alive. No technology we know how to build today can keep a human body intact for that span. Not freezing, not stasis, not generation ships. All of these remain at the level of speculation, with profound unsolved problems in every direction, so you can choose your method of failure. You can go slow, in which case the trip takes longer than civilizations last. You can go fast, in which case the energy required becomes astronomical, and the shielding requirements become extreme. You can go very fast, in which case time dilation isolates you forever from the world you left. There is no comfortable solution. There is no method by which a human being can simply visit another star the way they might visit another country. The universe is built to prevent that. The distances are not arbitrary. They are physical. They are made of trillions of kilometers of vacuum, of relativistic effects that bend time, of energy curves that climb toward infinity, of dust grains lurking like landmines, of cold so deep it freezes molecular motion itself. 1 light-year. Just one. And here is the truly terrifying part. We have not even left our own backyard. Because the sun's gravitational influence does not end at Pluto. It does not end at the Kuiper Belt. It does not end at the heliopause, where the solar wind finally surrenders to the pressure of interstellar gas. The sun's true gravitational territory extends out into a vast spherical halo of icy debris called the Oort cloud. And the Oort cloud, depending on which estimate you trust, stretches outward from roughly 2,000 astronomical units to as far as 100,000 astronomical units. 100,000 times the distance from the Earth to the Sun. That outer edge is approximately 1.6 light-years. Take a moment to absorb what this means. The entire bubble of space in which our sun's gravity still meaningfully reigns, in which objects still orbit our star rather than wandering freely through the galaxy, extends out to roughly 1.5 light-years. The boundary of the solar system is approximately the same distance we have just spent this entire conversation describing as nearly impossible to cross. To leave the solar system properly, not the inner solar system, not the planetary region, but the actual gravitational domain of the Sun, you must travel 1 light-year and then some. Voyager 1, which we keep returning to because it is the only object we have that even pretends to be on this kind of journey, is currently about 165 astronomical units from the Sun. That is approximately 0.0026 light-years. Voyager 1 has been traveling continuously for nearly 48 years and has covered roughly 1/400th of the distance to the outer edge of the Oort cloud. At its current speed, it will not reach the inner boundary of the Oort cloud for another 300 years. It will not pass through the outer boundary for somewhere between 20,000 and 30,000 years. In other words, the spacecraft that humanity launched in 1977 to leave the solar system will not actually leave the solar system, in the strictest gravitational sense, until the year 30,000 or later. That spacecraft was designed to last decades. Its plutonium power source has been gradually decaying since the moment of launch. By the time it crosses 1 light-year, it will have been a cold, dead piece of metal for tens of thousands of years. Its messages will have stopped. Its instruments will be silent. The golden record bolted to its side will be drifting through the dark, untouched, unplayed, unheard. The entire civilization that built it long since transformed beyond recognition. So when we say that crossing 1 light-year is hard, what we actually mean is something more disturbing than it first sounds. We do not mean that we cannot send something to a distant star. We mean that we cannot even confidently send something to the boundary of our own solar system in any time frame meaningful to the species that builds it. The light year is not the gap between us and another world. The light year is the radius of our own gravitational influence. It is the size of our address, and we cannot cross it. Now, what is in that space? In the trillions of kilometers between the orbit of Pluto and the far reaches of the Oort cloud, what exists? Almost nothing. Astronomers estimate that the Oort cloud may contain anywhere from 1 to 2 trillion icy bodies of various sizes. That sounds like a lot. Trillions of objects sounds like a crowded place. But they are spread across a spherical shell that is hundreds of millions of times larger in volume than the inner solar system. If you stood on one of these Oort cloud objects and looked around, you would see nothing. Just stars in the distance. Just a faint pinprick of light where the sun used to be. No brighter than the brightest stars you can see from Earth. The nearest neighboring Oort cloud object might be tens of millions of kilometers away. Possibly hundreds of millions. You would be alone in a way that no human has ever been alone. Not surrounded by night, surrounded by absence. This is what an interstellar journey would actually look like. You would not be flying past stars and nebula and visible structures the way films like to portray it. You would not be weaving through asteroid fields or dodging cosmic obstacles. You would be moving through nothing, for years, for decades, for centuries. The sun would shrink behind you until it became indistinguishable from any other point of light. The destination star would grow imperceptibly larger. For most of the trip, both would look exactly the same. You would be suspended in a darkness so complete that the very concept of direction would lose meaning. There would be no landmarks. There would be no progress markers. There would be no way for the human mind to feel that movement was occurring at all. The astronomer Carl Sagan once observed that the universe is mostly made of nothing. He was not exaggerating. The space between the orbit of Earth and the orbit of Mars contains roughly 250 million kilometers of essentially nothing. The space between Saturn and Uranus contains close to 1.5 billion kilometers of nothing. The space between Pluto and the inner edge of the Oort cloud contains nearly 300 billion kilometers of nothing. And the space between the outer edge of our Oort cloud and the outer edge of Proxima Centauri's hypothesized Oort cloud, the space that constitutes the true uncharted region between stars, contains trillions of kilometers of nothing. Pure vacuum. Pure cold. Pure silence. A void so total that we have no real terrestrial analog for it. There is no place on Earth that is as empty as the most populated cubic meter of interstellar space. And in that emptiness, even moving at velocities that destroy the body, that violate the assumptions of every engineering tradition we know, that require energy outputs equivalent to entire industrial civilizations, you would still spend years inside that nothing before reaching the next thing. This is why the question of how we might ever cross 1 light-year is not really a technological question. It is a biological one. It is a civilizational one. It is a question about whether any creature evolved on a small wet planet to live for a few decades and remember its grandparents can ever meaningfully relate to distances measured in trillions of kilometers and durations measured in centuries. The answer, at least so far, is no. We cannot. Not as we are. Not in the bodies we have. Not on the budgets we possess. Not within the lifespans we are allocated. We are simply not built for it. Some have proposed that we should send our descendants instead. The generation ship is one of the oldest concepts in serious interstellar speculation. The idea is straightforward in principle and almost impossible in practice. You build an enormous self-contained vessel, large enough to support a stable human population for hundreds or thousands of years. You launch it at a modest fraction of the speed of light, perhaps a single %. You accept that the people who board the ship will never see the destination. Their children might not either. Their grandchildren might not either. Only some distant descendant, 50 or 100 generations removed from the original crew, would ever set foot on a world around another star. The engineering challenges of building such a ship are extreme. You need a closed ecosystem stable enough to recycle every gram of carbon, nitrogen, oxygen, and water for centuries without external resupply. You need radiation shielding sufficient to protect a long-duration human population from cosmic rays. You need redundant systems for every critical function, multiplied many times over, because no rescue is coming and no maintenance is available. You need agricultural production, medical care, psychological stability, social cohesion, and reproductive sustainability across many generations of confined living. You need to ensure that the cultural memory of why the ship exists, where it is going, and what to do upon arrival is preserved across cycles of birth and death and forgetting that may last longer than any continuous human institution has ever lasted. And you need all of this to function inside what is essentially a sealed tube hurtling through vacuum at relativistic adjacent velocities for centuries, with no possibility of repair from outside, no possibility of replenishment, no possibility of evacuation. The historical analog most often invoked is the European exploration of the New World, but the analog is wildly inadequate. A sailing ship crossing the Atlantic might be at sea for 2 or 3 months. A wagon train crossing the American plains might be on the trail for half a year. A wooden ship rounding Cape Horn might be voyaging for a year. These journeys, though brutal, were of a duration that one human lifetime could span entirely. The crew that boarded the ship was, in most cases, the crew that disembarked at the destination. They aged, they suffered, they sometimes died, but they were the same people. A generation ship is something different. A generation ship is a society in motion, a civilization in a bottle. Everyone who boards must accept that the journey is the entirety of their existence. They will be born inside the ship. They will fall in love inside the ship. They will raise families inside the ship. They will grow old inside the ship. They will die inside the ship. They will never see the world their grandparents were promised. The choice their ancestors made to leave Earth becomes, for them, a fate they did not choose. A destination they may not even believe in by the time they inherit it. The ethical questions surrounding this are profound and largely unresolved. Do you have the right to condemn unborn generations to a sealed habitat moving through the dark simply because their ancestors signed up for a mission? What happens when, 3 centuries into the journey, the 7th-generation descendants of the original crew decide they do not want to continue, that they want to turn around, that they question the entire enterprise? You cannot turn around. The fuel was calculated, the trajectory was set. The deceleration burn at the far end was planned by people who died 200 years ago. The ship is on rails. The descendants are passengers in a journey they did not choose, headed for a destination they cannot reach, controlled by decisions made before they existed. And this is assuming everything goes well. History does not give us much confidence that closed societies survive across many generations without fracturing. Even on Earth, with the entire planet as a resource, with constant external input of energy and ideas and biology, human societies routinely collapse, fragment, or transform into something unrecognizable across timescales much shorter than what a generation ship would require. A self-contained colony of a few thousand people sealed inside a metal cylinder for a millennium would face challenges that no human community has ever survived. Political instability, genetic bottlenecking, religious schisms, mental health crises, infrastructure decay, knowledge loss. Each of these has destroyed civilizations on Earth in much shorter time frames and with far more resources available. So perhaps generation ships are not the answer. Perhaps we should consider freezing the crew instead. Cryopreservation, suspended animation, biological stasis. Put the travelers into a state where biology pauses, where the body does not age, where the mind does not perceive the passage of time, and then revive them on arrival. The journey, however long it takes, would feel instantaneous to the people inside. The trouble is that this technology does not exist. Not at the scale required. Not for human beings. Not for any large mammal. We can vitrify certain cells, freezing them with chemical protectants to prevent the formation of damaging ice crystals. We can preserve embryos. We can keep tissue samples viable for transplant. But preserving an entire adult human body in a state from which it can be revived intact, with the mind unchanged, the memories unaltered, the personality continuous, has never been demonstrated. There are unsolved problems at every level. The cellular damage from freezing, the chemical toxicity of cryoprotectants at the concentrations needed to prevent ice formation, the vascular fractures that occur during cooling, the neuronal degradation during long-term storage, and above all, the question of how to thaw, how to restart a biological system that has been functionally paused for centuries without losing the very thing that makes it a person. Many people, when they think about cryonics, imagine that the problem is simply one of cold storage, as if you could freeze a body the way you freeze a chicken and put it on a shelf and revive it on demand. But biology is not like that. Biology is a continuous chemical process. The moment that process stops, decay begins. Even at extremely low temperatures, even in deep vacuum, even in the cleanest possible storage conditions, slow degradation continues over centuries. Radiation steadily damages DNA. Cosmic rays passing through the body damage proteins. Slow molecular drift undoes structures that took a lifetime to build. And the longer the storage, the more accumulated damage there is to reverse. To preserve a human across a multi-century interstellar journey would require not just a freezing technology, but an active repair technology, a system capable of correcting damage faster than it accumulates, maintaining the biological pattern of the person through processes we have not yet imagined. We do not have this. We are not close to having this. Every research program in this direction is, at best, in the foundational stages, so perhaps we should not send humans at all. Perhaps the journey across a light year, and certainly across multiple light years, is fundamentally a task for machines. Robotic probes, artificial intelligence, self-repairing systems that can operate for centuries in deep cold and deep dark without the fragility of biology. This is, in fact, the direction most serious interstellar mission concepts have moved. Breakthrough Starshot, for instance, did not propose sending a crew. It proposed sending tiny sail-driven probes the size of postage stamps, accelerated by ground-based lasers to roughly 20% the speed of light, designed to fly past Proxima Centauri and beam back whatever data they could collect in the few hours they had during the flyby. No life support, no human cargo, just instruments, just observers, just messengers. This is more achievable. Not easy, not solved, but more achievable than the alternative. A small enough probe can be accelerated with manageable energy. A simple enough payload can survive interstellar dust impacts if the engineering is right. A short enough mission profile can be completed within the lifetime of the team that designs and launches it. The probe might take 20 years to arrive at Proxima Centauri. The data might take another 4 years to make its way back at the speed of light. The total mission, from launch to first results, might span less than a single human career. This is the upper limit of what current human civilization can reasonably attempt, and even this is enormously hard. The energy required for the laser array is staggering. The precision required to keep the laser focused on the sail across millions of kilometers is unprecedented. The sail material has to be reflective enough to ride the laser without melting, light enough to accelerate, and durable enough to survive the journey. The instruments on the probe have to be small enough to fit on a chip and sensitive enough to gather meaningful data from a brief flyby. The communication system has to be capable of transmitting that data across 4 light-years to a receiver on Earth using power so small it can be measured in fractions of a watt. Every one of these problems is at the bleeding edge of what is theoretically possible. But the point is that, even in the best-case scenario, even with all of these problems solved, what we are talking about is a small disposable probe that flies past a single star and dies. Not a return mission. Not a settled colony. Not a sustained presence. Just a brief glance at the next-door neighbor and a fading signal sent home before the spacecraft is forever lost to the dark. And in that fading signal, all of the romance of space exploration that fueled the 20th century begins to fracture. We did not grow up imagining flybys. We grew up imagining footprints. The Apollo missions did not just take pictures of the moon. They left tools and equipment and a flag. They walked on the surface. They drove a rover. They came back. The cultural memory of space exploration that we inherited is built on the assumption that humans go places, that the universe is, in some real sense, accessible. The reality of even 1 light-year reveals that the universe in another, equally real sense, is not accessible. Not to us, not in our bodies, not in our lifetimes, not with our energy budgets. The universe is open to data but closed to flesh. Information can cross light years, given enough time. People cannot. This is not a temporary limitation of our current technology. This is a structural feature of the cosmos. The speed of light is an upper bound enforced by relativity itself. Energy requirements for acceleration grow toward infinity. Time itself bends and isolates. The interstellar medium pelts everything in its path. The vacuum extends for trillions of kilometers in every direction. These are not engineering problems waiting to be solved by clever inventors. These are properties of the universe we live in, and 1 light-year is the smallest meaningful interstellar unit, the radius of our gravitational neighborhood, the distance to nowhere in particular. The space between us and the second nearest star to our Sun, after the Alpha Centauri system, is much greater than 1 light-year. Barnard's star is 6 light-years away, Wolf 359 is approximately 8 light-years away, Sirius is 8.5. Most stars in the Milky Way are tens of light-years from us. Most habitable zone candidates that we have identified through telescopes are hundreds of light-years from us. The center of the galaxy is 26,000 light-years away. The far side of the galaxy is 100,000 light-years away. If crossing 1 light-year takes us 17,000 years at Voyager's speed, how long does it take to cross the galaxy? At Voyager 1's velocity, traversing the diameter of the Milky Way would take approximately 1,700,000,000 years, roughly 1.5 billion years. That is longer than complex multicellular life has existed on Earth. If the very first eukaryotic cells, the ancestors of every plant and animal and fungus, had launched a Voyager-style spacecraft at the moment they first emerged from the primordial sea, that spacecraft would still be in transit. It would still be crossing the Milky Way. It would not have arrived. The crossing of a single galaxy at the speed of the fastest object humanity has ever launched takes longer than the entire span of complex life. There are 2 trillion galaxies in the observable universe. This is the scale we are dealing with. This is the geometry of the cosmos. 1 light-year is the small unit, the trivial unit, the almost nothing unit. And we cannot cross it. So what does this mean for us? What does it mean to be a species that has discovered the size of the universe and discovered, simultaneously, that we cannot meaningfully traverse it? One reading is bleak. Some philosophers and astronomers have argued that the discovery of cosmic scale represents a kind of cosmic loneliness sentencing. We are confined to a single planet around a single star, possibly forever. The other stars are visible but unreachable. The other galaxies are detectable but utterly inaccessible. The universe is, in practice, a single small island of biology in a sea of empty distance. Whatever happens on Earth will be, in any meaningful sense, the whole of our story as a species. There is no escape hatch. There is no plan B. The stars are scenery, not destinations. Another reading is different. The same constraints that make the universe so hard to cross also mean that the universe is enormous beyond all proportion to anything we could fill with our presence. If we cannot cross 1 light-year, then there are vast spaces in which other lives, if they exist, can develop and evolve and rise and fall entirely without disturbing us. The same isolation that traps us also protects every other potential civilization. The dark forest is not just a metaphor about cosmic predators. It is a description of the structural privacy of the universe. Every star system is a sealed chamber, surrounded by trillions of kilometers of insulation. Nothing reaches anything. Nothing arrives. Nothing interferes. In a universe like that, the question of how often life arises matters far less than we tend to assume. Even if life is common, even if there are millions of biospheres scattered across the galaxy, the practical effect is the same as if we were alone, because we cannot meet them. They cannot meet us. The geometry of the cosmos enforces a kind of metaphysical solitude that has nothing to do with whether life is rare. It has to do with whether life is reachable And the answer, on the scale of 1 light-year, is no. This is the haunting truth that the light-year carries inside it. It is not just a unit of distance, it is a unit of separation, a unit of irreducible isolation. The light-year is the universe's way of saying that no matter how complex you become, no matter how clever your engineering, no matter how patient your civilization, the gulf between you and anything else is built from physics that cannot be negotiated. And yet, light itself does cross it. In 1 year, without effort, without acceleration, without fuel, without consequence, light pours from every star in every direction continuously, crossing 1 light-year after another, without slowing, without thinking, without caring. The galaxy is bathed in light that has crossed unimaginable distances. The universe is saturated with information that has traveled across distances we cannot reach. Right now, light from stars 1 light-year away is reaching your eyes if you walk outside and look up. Light from stars 1,000 light-years away. Light from stars 10,000 light-years away. Light that left its source when humans were still discovering fire. Light that left its source when there were no humans at all. That light has crossed everything. It has crossed the very distances we have spent this evening calling impossible. It crosses them constantly. There is something deeply strange about this. The universe is structured so that information flows freely across the void at the speed limit of reality, while matter, particularly the kind of complex organized matter we call life, is essentially frozen in place. Photons can travel, atoms cannot. Knowledge can move, bodies cannot. The cosmos is set up like a library that anyone can read but no one can enter. This is why astronomy works at all. It is the only science in which we can study things we can never visit. Every other field of investigation is grounded in the possibility of contact. A geologist can go to the rock. A biologist can examine the organism. A chemist can mix the substances. But an astronomer studying a galaxy 10 million light-years away will never see it directly, will never touch it, will never visit it, will never receive a sample from it. Everything we know about every star and every galaxy we have ever studied comes from photons. From light that left those objects and crossed the void, and finally, after journeys that often dwarf the existence of human civilization, arrived at a telescope on Earth or in low orbit. We are not exploring the universe, we are listening to it, we are reading its broadcasts. We are pressing our ears against the door of a room we will never enter. This is the strange double truth of the light year. It is both a wall and a window. It blocks us from moving and it lets us see. It traps our bodies in our birthplace, and it carries information from the entire cosmos to our doorstep. The universe is open to perception and closed to participation. Open to the eye and closed to the foot. And perhaps that is the only relationship we will ever have with what lies beyond. Perhaps the human role in the cosmos is not to colonize, but to comprehend. Not to expand, but to understand. Perhaps the species that builds telescopes that can see 13 billion light-years into the past, that can map the positions of 2 trillion galaxies, that can detect the faint afterglow of the Big Bang itself, has already done something far more remarkable than any colonization could ever accomplish. We have made the universe legible. We have read its outlines, learned its history, calculated its age, traced its structure. We have done this from a single fragile planet, with telescopes built from materials we mined from our own crust, with mathematics developed by our own thinkers, with imaginations evolved on the savannah. That is the consolation, if there is one. We may never cross a light-year, but we have learned what a light-year is. We have measured how many of them surround us. We have mapped the structures that fill the volume of the observable universe. We have, in our minds and in our instruments, embraced a scale we will never personally inhabit. Still, sit with the discomfort for a moment longer. Because that consolation is not the whole story. The fact that we can see the universe does not change the fact that we are not in it, in any active sense. We are observers. We are not participants. The drama of the cosmos unfolds across distances we cannot cross, on timescales we cannot endure. And one of the things that drama might include is other observers, other minds, other species who have also looked up at their own stars and asked the same questions and run the same calculations, and arrived at the same terrifying answer about 1 light-year. If they exist, we will probably never know. Not because they are hidden, not because they are silent, Because the distances between us are designed, by the structure of the cosmos itself, to prevent connection. They have their light year too. They have their Oort cloud and their Voyager, and their cryogenic dreams and their generation ship anxieties. They have looked at the energy curves and the radiation problems and the interstellar dust and arrived at the same conclusion. They are stuck. We are stuck. Everyone is stuck. This is the Great Silence reinterpreted. Not as an absence of life, but as a property of geometry. The cosmos does not need to actively isolate civilizations. The cosmos is isolation. The light year is the wall, and the wall is the universe. But there is one more layer to this that I want to draw out before we move on. Because while we have been talking about crossing a light year, we have been assuming that crossing means traveling, movement, transit, a body or a probe moving from one point to another. There is another sense in which we might cross a light year, and it is far more accessible. Every time you look up at a star, you are receiving photons that have crossed many light years to reach your eyes. Those photons traveled across the same dark, cold void we have been describing as nearly impossible to traverse. They made the crossing. They arrived. And when they entered your eye, when they triggered the photoreceptors on your retina, when they sent a signal through your optic nerve to your brain, you became, in that moment, the endpoint of an interstellar journey. The light completed a trip we cannot make, and it ended its journey in you. This is not a metaphor. This is literal physics. A photon emitted from Proxima Centauri left that star 4 years ago. It traveled across 40 trillion kilometers of vacuum. It dodged interstellar dust and avoided gravitational deflection and survived the slow stretching of space itself. And then it ended its existence by being absorbed by a cell in your eye. You are, in a real and measurable sense, the destination of an interstellar voyage every single time you see a star. The crossing is not theoretical. It happens billions of times per second to every person who has ever opened their eyes under a night sky. We are not entirely separated from the cosmos. The cosmos is reaching us, constantly, in small fragments, in particles of light that have crossed everything we cannot. We are bathed in interstellar travelers. We are surrounded by photons that have completed journeys longer than the age of our species. We are, in some sense, in continuous contact with the rest of the universe, just not in the way we usually imagine. The light year is impassable for us, but it is the daily commute for light. And the light is here, right now, touching everything. But touch is not the same as conversation. And the asymmetry between what reaches us and what we can send back is one of the cruelest facts the universe has to offer. When you look at a star 1 light year away, you are seeing it as it was 1 year ago. That is not a poetic statement. That is a hard mechanical fact about how photons travel and how time and distance interact. The star may have changed in that year. It may have flared. It may have darkened. It may have ejected mass. You will not know for another year. The information is in transit. It is making its way across that same trillion-kilometer gap. There is nothing you can do to hurry it. The universe will not give you a preview. This is the temporal price of distance. Every light year between 2 points is also 1 year of delay. Every observation we make of any distant object is, by physical necessity, an observation of that object's past. We cannot see anything as it is right now. We can only see it as it was when its light departed. For nearby objects, this is barely noticeable. The light from the moon takes about 1.3 seconds to reach us. The light from the sun takes a little over 8 minutes. When you look at the sun, you are seeing it as it was 8 minutes ago. If the sun were somehow extinguished at this very second, you would have no idea for another 8 minutes. The sky would remain bright. The day would continue. Earth would keep orbiting along a curved path that no longer exists. Only after 8 minutes would the news arrive, in the form of darkness sweeping across the daylight side of the planet. The gravitational pull would also vanish at the same moment, traveling at the speed of light. Suddenly, Earth would lurch into a straight-line trajectory through the cold of an empty solar system. That 8-minute delay is already disturbing to think about. The sun is by far the most important object in our daily lives, and we are looking at a recording of it. We are watching what the sun did, not what it is doing. Now, scale that delay up to a light year. A star 1 light-year away is being watched from a perspective that is 12 months out of date. Any flare it produces today, we will not see until next year. Any change in its brightness, any shifting of its surface features, any planetary transit, any catastrophe in its system is happening in a present we cannot access. We have to wait, and by the time the information arrives, that information itself is also already a year old. By the time it reaches our instruments, there is no way to peek. There is no way to fast forward. There is no way to catch up. The universe has built into its laws a kind of temporal moat that places every distant point at a permanent remove from our actual now. Some people, when they first encounter this idea, ask whether some clever physics might let us bypass it. Quantum entanglement comes up most often. The idea is that two entangled particles, separated by any distance, share a correlated state that updates instantaneously when one is measured. Surely the intuition goes, this means we could send information faster than light. Surely entanglement lets us bridge the gap. It does not. This is one of the most stubbornly misunderstood aspects of quantum physics. Entanglement creates correlations between particles, but it does not allow the transmission of information. The measurement of one entangled particle gives a result that is in some sense linked to the result of measuring its partner, but neither observer can use that correlation to send a message. The pattern of measurements on each side, examined in isolation, looks completely random. It only reveals its structure when the two sets of measurements are compared, and that comparison requires sending classical information from one location to the other. And classical information cannot travel faster than light. So entanglement does not provide a faster-than-light communication channel. It cannot. The no-communication theorem in quantum mechanics is rigorous and well-established. It is not a limitation of current technology. It is a feature of how the universe is built. Other proposed faster-than-light methods have similar problems. Tachyons, the hypothetical particles that always travel faster than light, have never been detected and would create paradoxes if they existed. Wormholes are mathematically permitted by general relativity, but they require exotic matter with negative energy density that has never been observed in macroscopic form, and stabilizing one against collapse would demand engineering on scales we cannot even simulate. The Alcubierre drive, the most famous warp drive proposal, requires similar exotic energy conditions and asks us to compress and stretch space itself in ways that may or may not be physically possible. None of these are practical solutions. They are theoretical curiosities that may or may not survive future revisions of physics. So we are stuck with the speed limit. The universe enforces it. Every photon obeys it. Every signal we have ever sent or received has obeyed it. And the speed of light, in cosmic terms, is slow. Not slow compared to anything we usually experience, but slow compared to the distances the universe has put between things. This is why 1 light-year matters as a unit. It is the smallest distance at which the speed of light starts to feel slow. It is the threshold at which conversation becomes impossible. You cannot have a real-time exchange with anyone 1 light-year away. You can send a message, they can receive it a year later, they can reply. You can receive the reply another year after that. A single round of conversation takes 2 years. A more elaborate dialogue would take decades. The very structure of dialogue, the rhythm of back and forth that defines human communication, breaks down at interstellar distances. There is no chatting with the stars. There is only delayed correspondence with absurdly long mailing times. Now imagine this from the perspective of an actual interstellar mission. A probe traveling toward a star 4 light-years away. As it moves, it sends data back to Earth. But every transmission is years out of date by the time it arrives. Mission Control on Earth issues commands based on what the probe was doing 4 years ago. The probe receives those commands 4 years after they were sent, by which time the situation may have changed completely. Decisions cannot be made interactively. The probe must operate semi-autonomously, anticipating problems and solving them locally, because by the time anyone on Earth knows what is happening, the moment of intervention is long past. This is already true at the scale of our solar system. The Mars rovers operate with significant communication delays, between 4 and 24 minutes one way, depending on planetary positions. Operators on Earth cannot drive the rovers in real time. They send a packet of commands at the start of a Martian day. The rover executes them. The next packet arrives the following day. Driving Curiosity or Perseverance is more like programming a remote agent than steering a vehicle, and these delays are only minutes. At 1 light-year, the delay is a year. At 4 light-years, 4 years. At 1,000 light-years, 1,000 years. Any civilization sending probes into deep interstellar space is sending them on missions that fundamentally exceed the speed of human dialogue. The probes become not extensions of our awareness, but ambassadors to a future we will not personally witness. They are time capsules in motion. They go out, they explore. Their reports arrive years or decades later, addressed to whoever happens to be staffing the receiver that day. The original mission team may be retired, may have died, may have been forgotten. The data still comes back, the data does not care. This temporal distortion is what makes interstellar communication, even before we discuss interstellar travel, an exercise in patience that pushes against the boundaries of what human institutions can sustain. We are not used to projects whose payoff comes after the project's originators are gone. There are exceptions. Cathedrals were built that way. So were certain forestry projects. So were ancient road systems. But these were embedded in cultures with longer time horizons than ours. Modern industrial civilization is structured around quarterly reports and election cycles and product launches measured in months. The very idea of building something whose first results will arrive in 50 years is alien to the rhythms of contemporary life. And 50 years is fast for interstellar work. A genuine mission to Proxima Centauri at any plausible velocity is a multi-decade undertaking before the first data arrives. A mission to a star 10 light-years away, even at 20% the speed of light, is a 50-year mission. A mission to a star 100 light-years away, at the same speed, is a 500-year mission. We are not equipped, as a culture, to commit to projects on those timescales. We do not have institutions that reliably persist for centuries. The very organizations that would have to track the probe, receive its data, and analyze its findings might not exist by the time the probe arrives. The receiving antennas might be obsolete. The data formats might be unreadable. The mission might fail, not because the spacecraft fails, but because the receiving end of the connection has decayed. Consider, briefly, what would be required for a civilization to actually conduct a meaningful interstellar mission. It would need to maintain a single coordinated effort across centuries. It would need a chain of institutional continuity longer than most empires have ever managed. It would need to fund and staff a project whose results would be enjoyed by descendants the original workers would never meet. It would need to commit, in advance, to a goal that could not be revised, recalled, or canceled once underway, because the probe is in flight and cannot be retrieved. It would need a culture in which long-term thinking is not merely valued, but structurally enforced. Looking at human history, this seems unlikely. Our species has occasionally produced institutions that lasted for centuries. The Catholic Church, the Imperial Chinese examination system, a few universities, a few monasteries. But these are exceptions. Most political entities, most companies, most cultural institutions change beyond recognition or vanish entirely within a few generations. The idea that our species could sustain a focused technical effort across the time required to send a probe to a distant star and receive its data is, by historical standards, ambitious to the point of implausibility. This raises a deeper question. Perhaps the limits on interstellar travel are not really limits of physics at all. Perhaps they are limits of civilization. Perhaps the universe is full of species who could, in principle, build probes capable of crossing light years, but who cannot sustain the institutional commitment to actually do so. The bottleneck is not propulsion. It is patience. It is the cultural capacity for projects that extend beyond a single human lifetime, beyond a single political era, beyond a single technological epoch. If this is the bottleneck, then the silence of the cosmos starts to take on a different shape. It is not that no one is out there. It is that no one stays focused on the problem long enough to make the journey. Civilizations rise. They develop technology. They become aware of the scale of the universe. They calculate the energy required to cross a light year. They consider the timescales involved. They decide, often quite reasonably, that other priorities are more pressing. and they turn their attention inward. They solve problems at home. They build comfortable lives within their gravitational well. They never quite make the leap. If this happens consistently, then the universe could be teeming with intelligent species and still appear empty from any single observer's perspective. Every species would be sitting in their own home system, looking out at stars they could in principle reach but have never quite gotten around to reaching. The night sky of each civilization would look mostly empty for the same reason ours does, not because no one is there, but because making the journey is harder than staying still, and 1 light-year is the smallest piece of that journey, the unit that demonstrates the problem, the threshold at which the difficulty becomes undeniable. Let us think about this in a different way. Let us consider what 1 light-year would look like if you tried to walk it. A human being walks at roughly 5 kilometers per hour. If you walked for 8 hours every day, you would cover 40 kilometers per day. That is about the distance a fit hiker can manage on a long trail. Over a year of daily walking, you would cover roughly 15,000 kilometers. That is enough to walk across an entire continent multiple times. A truly heroic distance by any human measure. To walk 1 light-year, you would need approximately 631 million years. 631 million years. Compare that to the age of life on Earth. Multicellular life has existed for about 1 billion years. Animals with shells appeared about 540 million years ago. The first land plants emerged about 470 million years ago. The first dinosaurs appeared about 230 million years ago. The asteroid that ended the age of dinosaurs struck Earth about 66 million years ago. The first hominins appeared about 7 million years ago. Anatomically modern humans appeared about 300,000 years ago. If you had started walking 1 light-year before the present, you would have begun your journey before complex animals existed on Earth. Before fish. Before insects. Before the first land plants colonized continents. The entirety of multicellular evolution would have occurred during your walk. You would have stepped across the boundary of the Cambrian explosion. You would have walked through the entire reign of the dinosaurs. You would have witnessed the slow drift of continents into their modern configurations. You would have walked through ice ages and warm periods and supercontinents forming and dissolving. And you still would not have finished. You would still have more walking ahead of you, many millions of years of additional walking. That is 1 light-year on foot. Of course, no one walks across vacuum, but the absurdity of the comparison is useful because it grounds the number in something the body can feel. Even the most committed effort of a single human body, sustained for the duration of complex life on Earth, would not cover 1 light-year. The body is simply not designed for that distance. No biological organism is. There is no way to scale up from a walking pace to interstellar distances through endurance alone. This is why the only realistic discussion of crossing light-years involves machines. Not because biology is uninteresting, but because biology operates on timescales that are vanishingly short compared to the distances involved. A human body lasts perhaps 100 years. A light-year requires hundreds of thousands of years to cross at our fastest speeds. The mismatch is roughly a factor of 10,000. We would need to either extend the body by 4 orders of magnitude or compress the journey by 4 orders of magnitude. Neither is on offer. Some have suggested that artificial intelligence might be the answer, a sufficiently advanced machine intelligence, durable enough to survive centuries of interstellar transit, might be able to make the journey in a way that biological humans cannot. The mind, if it could be encoded in resilient hardware, would not need to age the way bodies age. It could be paused, it could be slowed, it could be powered down for the duration of the trip and reactivated upon arrival. A digital consciousness, in principle, has fewer obstacles to long-duration interstellar travel than a biological one. This is a more plausible scenario in some ways than the generation ship or the frozen crew. A self-contained artificial mind aboard a small spacecraft, with redundant hardware, self-repairing systems, and a vast knowledge archive, might be able to survive a multi-century crossing. It might arrive at a distant star still functional. It might begin operations. It might send back data. It might, depending on its capabilities, build infrastructure at the destination using local materials. But this raises its own set of problems. Are we still talking about human exploration if the explorers are artificial minds? Are they extensions of our species, or a different kind of intelligence entirely? Are we sending ourselves to the stars or sending our successors? If our successors do the exploring, do we ever, in any meaningful sense, leave Earth? These questions matter because the dream of interstellar travel has always been more than a logistical project. It has been a fantasy of presence, of human bodies in alien places, of children born under alien suns, of the species expanding into a larger cosmos. If the actual physical journey can only be made by machines, then the fantasy collapses into something quieter. We do not become a galactic species. We become a species that built galactic instruments. Our descendants do not walk on alien worlds. Our probes scan those worlds and send back information. And even those probes will be alone. They will travel for centuries through dark space, communicating with a planet that may not remember why they were launched. They will arrive at their destinations and report back to a civilization that has either changed beyond recognition or no longer exists. They will be the only meaningful interstellar travelers our species ever produces. And they will not know they are doing anything special. They will simply execute their programs in the deep cold of the void, performing their measurements, transmitting their data, drifting onward into whatever lies beyond the first crossing. This is the practical answer to the question of how we cross 1 light year. Not with bodies, not with crews, not with colonies, with small patient machines that will outlast everyone who built them and will arrive at their destinations long after their creators are gone. It is not the answer most of us want. The myths of space exploration, woven through 20th century culture, promised something else. They promised that humans would walk on Mars by the year 2000, that we would have colonies on the Moon by 2010, that we would visit other star systems within a few generations. None of that has happened. None of it is going to happen on those timelines. The myths were not lies, exactly, but they were dreams unconstrained by the actual physics of the universe. The actual physics is harsher. The actual physics says that 1 light year is essentially the limit of what we can hope to send anything to within a single human lifespan. And even that requires technologies we do not yet have. This is not a failure of imagination. It is a recognition of what the universe is. The universe is large. The light year is its small unit of largeness. And we are, despite our cleverness and our ambition and our long history of mastering the world around us, very small compared to it. There is something almost vertiginous about looking up at a star and realizing all of this at once. That the star you are seeing is one of the closer ones, and even it is essentially out of reach. That the light reaching your eye traveled for years to get here. That if you wanted to go visit, you would die long before the journey could be completed. That the universe is built in a way that prevents your kind of body from ever standing on the surface of another star's planet. The night sky, viewed with this knowledge, becomes both more beautiful and more isolating. Each point of light is a place we cannot go, a community of warmth and gravity and possibly life that is forever sealed off from us by the unyielding mathematics of speed and distance. And yet we keep building telescopes. We keep mapping the cosmos, we keep refining our understanding. There is something in our species that cannot accept the inaccessibility as final. Even when we know the answer, even when the energy budgets and the timescales make it clear that crossing 1 light year is impossibly difficult, we continue to plan. We continue to design. We continue to ask whether the next propulsion concept might just barely make it work. The dream does not die because it is impractical. It persists because something in us refuses to settle for the simple truth that the universe is mostly out of reach. Maybe that refusal is itself important. Maybe the very impossibility of interstellar travel makes the attempt more valuable, not less. Civilizations that direct their attention only at what is possible tend to stagnate. Civilizations that reach beyond their grasp sometimes accomplish things that change what is possible. The Apollo program seemed impossible to many serious analysts in the late 1950s. It happened anyway. Not because someone discovered new physics, but because a society decided to organize itself around an outcome that was not yet within reach. The decision came first. The technology followed. It is possible, though not certain, that something similar could happen with interstellar travel. A society sufficiently committed to crossing the light-year barrier might develop the technologies needed to do it. Not necessarily the technologies we have imagined. Possibly technologies we cannot yet imagine. The history of science is full of breakthroughs that seemed unreachable until they happened. The early 20th century had no concept of nuclear energy. The early 21st century has no clear concept of how to safely cross a light year. But that does not mean the puzzle is permanent, it means it is unsolved. What we can say is that the problem is real. It is not exaggerated. 1 light year is not a small number wearing a big costume. It is a genuinely enormous distance, encoding genuinely impossible energy requirements at any speed that would make the journey feasible within a human time frame. The challenge is structural. It is not a matter of waiting for the next generation of rockets. The next generation of rockets, however impressive, will still face the same fundamental problem. The problem is the distance. The problem is the speed of light. The problem is that the universe is large in a way that has no analogy in our daily lives. And maybe that is the final lesson of the light year. It is not just a unit of distance. It is a unit of perspective. It is a yardstick that, when held against the cosmos, reveals how much of the universe lies beyond our practical reach. It is a humility delivered in kilometers. A reminder that everything we have accomplished as a species, every empire we have built, every discovery we have made, has happened within a tiny gravitational pocket so small that on the scale of the galaxy it would not even register. Our entire civilization fits inside a sphere of influence that is, at best, a tiny fraction of 1 light year across. We have not gone anywhere yet. We have peeked over the edge of our cradle and seen how vast the room is. And the room is not even the building. The building is not even the city. The city is not even the country. There are scales upon scales of largeness extending outward from us, and 1 light year is the first marker on that journey. The first wall. The first reminder that the universe is built on dimensions that do not care how clever we are. If we ever do cross it, it will not be soon, it will not be easy, it will not be cheap, it will not be glamorous. It will probably be a small probe carrying instruments communicating back across a fading link, observed by a civilization that will be very different from the one that launched it. The crossing will happen, we just will not be there to feel it. And so we are left, for now, with photons. With light arriving constantly from places we cannot go, carrying news we cannot answer. The universe writes us letters. We read them. We cannot reply. The conversation, for all its richness, is one-sided. The cosmos sends. We receive. But maybe that is enough. Maybe being on the receiving end of a continuous stream of interstellar correspondence is itself a kind of participation. We are not visiting the cosmos, but the cosmos is visiting us. Through every photon, through every wavelength, through every faint signal our telescopes can extract from the noise of space. The universe is here, in the form of light, even if we are not there, in the form of bodies. And the light, having crossed 1 light year or 1 million light years, is real. It is not a representation. It is the actual physical material of the universe arriving on our doorstep, after journeys that began before anything we recognize as human had emerged from the dust. Sit with that for a moment. Tonight, when you look up, the photons entering your eyes are completing journeys longer than the existence of agriculture, longer than the wheel, longer than written language, longer than fire using hominins. They are crossing the very distances we have just spent these hours describing as terrifying. They cross them constantly in vast, quiet floods, all the time, everywhere, without effort, without acknowledgement, without ceremony. The terror of 1 light year for them is not a terror at all. It is simply the next thing to cross. For us, the next thing to cross is a wall. For light, it is a hallway. And the difference between those two relationships, with the same distance, reveals something profound about what kind of thing we are. We are made of matter. Specifically, we are made of complex arrangements of matter that carry within them the rules of biology. Cells, tissues, organs, nervous systems, memories, identities. All of this is structured atoms, holding together in patterns that took billions of years to evolve. And all of this is fragile. It needs warmth. It needs water. It needs oxygen. It needs a particular range of pressure and temperature and radiation exposure. It needs to keep moving in a particular way at a particular rate, or it stops being what it is. Stop the heart for a few minutes. The pattern collapses, Cool the brain too far, the pattern collapses. Bombard the body with too much radiation, the pattern collapses. There is no version of our particular kind of matter that can simply endure indefinitely. Time wears it down. Distance kills it. Light does not have this problem. Light is not made of complex arrangements that have to maintain themselves. A photon is itself, fundamentally, without metabolism, without dependencies, without aging in any meaningful sense. A photon traveling for 10 billion years is the same photon at the end of its journey that it was at the beginning, save for a slight stretching of its wavelength by the expansion of space. It does not get tired. It does not need to eat. It does not require shielding. It does not have memories that could be lost. It is information moving through vacuum at the speed limit of the universe, and the universe does not charge it for the trip. Matter and light are both real. They are both physical. They both exist according to the same fundamental laws. But the universe treats them very differently. Light is welcomed. Matter is barely tolerated. Light passes freely through the gulfs between stars. Matter has to fight every kilometer. This is one of the strangest features of the cosmos we inhabit. The thing we are made of is the thing the universe wants to keep in place. The thing we use to learn about the universe is the thing the universe lets go everywhere. We are stationary observers in a sea of moving information. We sit still. The light comes to us. And it is in this asymmetry that the terrifying reality of crossing 1 light-year really lives. Not in the size of the number. Not in the slowness of our spacecraft. Not in the energy curves of relativity. Those are symptoms. The deeper truth is that we are the wrong kind of thing to make these journeys. The universe makes them, constantly. But it makes them with photons, not with people. The architecture of physical law privileges light over flesh. And flesh, watching the light arrive from places it can never visit, has to make peace with that privilege somehow. Some people, when they confront this fact, become quiet. Some become dismissive. Some refuse to accept it and insist that future technology will solve everything. Some take refuge in metaphors. Some lean on faith in one form or another that the limits we see now are not the limits that will always hold. And it is true that we cannot rule out future surprises. The history of physics has involved many shocks, but here is what we have to be honest about. Every time a surprise has expanded our understanding, it has not been by overturning the basic structure of relativity. Relativity has been tested and retested at extraordinary precision for over a century. Every measurement we have ever made confirms it. Every prediction it has produced has held. Time dilation, length contraction, mass energy equivalence, gravitational waves, the bending of light around massive objects, the behavior of GPS satellites that have to account for relativistic corrections in order to give you accurate directions. All of it is real. All of it is observed. All of it has been incorporated into the working theory of how the universe operates. The speed of light is not a wall waiting to be broken. It is the asymptote that our universe has built into its operational logic. So when we ask whether crossing 1 light-year is hard, we are not asking a contingent question. We are not asking whether the engineering is currently insufficient. We are asking a question whose answer is woven into the fabric of physical law. The answer is yes. It is hard. It is hard in a way that goes deeper than technology. It is hard because the universe has set up its rules to make it hard. Imagine, just to make the point concrete, what would happen if we did launch a probe at 20% the speed of light toward Proxima Centauri. The energy budget required is staggering, but suppose we manage it. The probe departs. From the perspective of someone on Earth, the probe takes about 21 years to make the crossing, plus another 4 years for the data to come back. Roughly 25 years from launch to first results. But from the perspective of the probe itself, if it had any awareness, those 21 years would not feel like 21 years. Time dilation would compress them slightly. At 20% the speed of light, the time dilation factor is small, only about 2%. The probe would experience roughly 20.5 years instead of 21. Not much different. The dramatic time dilation effects only kick in much closer to the speed of light. If we could push the probe to 99% the speed of light, The journey to Proxima Centauri would take about 4 years and 3 weeks from Earth's perspective. But from the probe's perspective, only about 7 months would pass. The probe would arrive having experienced just over half a year of travel time, while back on Earth, more than 4 years would have elapsed. This is the relativistic compression of long journeys. The faster you go, the less time you experience on the journey, even though the rest of the universe continues at its normal pace. At extreme velocities, you could in principle traverse vast distances in subjectively short times. A trip to a star 100 light-years away, made at 99.99% the speed of light, would take only about a year and a half from the traveler's perspective. But on Earth, more than a century would pass. This sounds like a solution to the interstellar problem. Go fast enough, and the journey shrinks. But the catch is brutal. You can never come home. The friends you left behind have aged 100 years. They are dead. Their children are old. Their grandchildren do not remember you. The world has moved on. Through cultural and political and technological transformations you did not witness, you arrive at your destination as a person from the past, dislocated in time, severed from everyone you ever knew, and this is at speeds we cannot remotely achieve. The energy required to push even a small object to 99.99% the speed of light is astronomical. We are talking about a fraction of the total power output of an entire star, focused with surgical precision for years. There is no engineering proposal currently on the table that achieves this. There is no theoretical pathway that gets us there using known physics, except by hand-waving past enormous practical obstacles. So the relativistic solution to interstellar travel exists in principle, but only in principle. It does not exist in any form we can build. And even if we could build it, the trade-off is the permanent severance from home. There is no version of this story in which we have our cake and eat it too. The universe simply does not offer that option. This brings us back again to the question of who actually crosses light years. The answer, in the world we live in, is photons. Light from stars 1 light-year away reaches us continuously. Light from stars 1,000 light-years away reaches us continuously. Light from galaxies billions of light-years away reaches us continuously. The information from across the cosmos is pouring into our telescopes every moment. We are awash in interstellar data, we just cannot return any of it. And here is the strange beauty of this situation. If you accept that we will not, in any conventional sense, physically traverse the universe, then what we have already done starts to look like something extraordinary. We are a species on a single planet that has, through the patient work of telescopes and theory, comprehended the structure of the cosmos out to distances of nearly 14 billion light-years. We have measured the age of the universe. We have mapped its expansion. We have detected gravitational waves from collisions of black holes in galaxies billions of light-years away. We have photographed the silhouette of a supermassive black hole at the heart of another galaxy. We have detected planets around stars hundreds of light-years from us. We have done all of this from a single, small world, using instruments we built with our own hands. The crossing of light-years is something we do every day, but we do it with our minds, not with our bodies. We do it with mathematics and instrumentation. We do it by being patient enough to receive the light when it arrives, and skilled enough to read what it carries. This is not the same as being there, but it is not nothing either. It is a real form of cosmic engagement that no other species on this planet, as far as we know, has ever achieved. Still, the original question stands. What if we wanted to be there? What if data was not enough? What if some descendant of ours, generations from now, still nursing the ancient itch to see other worlds with their own eyes, decided to commit serious effort to crossing 1 light-year? What would it take? It would take, first, a fundamental reorientation of civilization itself. The project would have to span generations. It would have to survive political turnover, economic crises, technological shifts, and cultural changes. The institutions overseeing it would need stability measured in centuries, not in election cycles. The funding would need protection against the routine pressure to reallocate resources toward more immediate concerns. The cultural valuation of the project would have to remain high across the entire duration, not just at the moment of inspiration. It would take, second, an immense expansion of energy infrastructure. To accelerate any meaningful payload to a meaningful fraction of the speed of light requires energy comparable to the total annual output of multiple advanced industrial civilizations. We would have to harvest energy on scales we currently do not approach. Some have suggested orbital solar arrays, fusion reactors of unprecedented power, or even partial Dyson swarms around the sun. None of these are concepts we know how to build. They are concepts we know how to describe. It would take, third, breakthroughs in propulsion that we have not yet made. Chemical rockets cannot do this work. Ion engines, while more efficient than chemicals, do not scale to relativistic velocities. Nuclear thermal propulsion gives us more thrust, but still falls far short. Antimatter propulsion is theoretically capable of producing enough energy density, but we do not know how to produce or store antimatter in the quantities required, and even if we did, the engineering challenges would be enormous. Laser-driven light sails like those proposed by Breakthrough Starshot can accelerate gram-scale probes but not larger payloads. Some form of propulsion that we do not yet have is required for anything beyond miniature probes, and we have no clear path to it. It would take, fourth, advances in materials science that allow spacecraft to survive sustained interstellar conditions, shielding against radiation, resistance to dust impacts, thermal management in the deep cold, redundancy against single-point failures across centuries of operation. All of this is harder than anything we have built for missions inside our own solar system. By orders of magnitude. It would take, fifth, autonomy systems capable of handling situations we cannot anticipate. A spacecraft traveling across light years cannot wait for instructions from home. It has to make its own decisions, it has to diagnose its own problems, it has to repair its own damage, it has to navigate, adjust, and survive in environments we have never tested anything in. This requires artificial intelligence well beyond what currently exists, embedded in hardware durable enough to last the duration. It would take, sixth, a destination worth the trip. We can imagine sending a probe to Proxima Centauri because we know there is at least one rocky planet there. Proxima Centauri b orbits in the habitable zone of the star. It might have an atmosphere. It might have water. It might host the conditions necessary for some form of biochemistry to operate. But it might also be a sterilized rock baked by stellar flares from its volatile parent star. We do not yet know. And the cost of going is so enormous that we have to be reasonably confident that what we find there will be worth the price of finding it. Better telescopes will help. The James Webb Space Telescope and its successors will reveal more about the atmospheres of nearby exoplanets. But the question of whether any specific destination is worth a multi-decade interstellar mission is still open. And it would take, finally, a willingness to send something that will never come back. The probe is one way. The data is one way. The journey is one way. Whatever we send forever. It is not a mission of return. It is a mission of dispatch. The civilization that launches it must accept that the probe will spend the rest of its existence in the dark, far from home, doing its work for a parent species it will never see again. When you list these requirements, you start to understand why no one has ever made an interstellar trip. Not because of any individual obstacle, but because of the convergence of all of them. To cross one light year is to demand from your civilization a list of capabilities and commitments that no civilization in the history of our planet has ever come close to assembling. And yet, on the other side of this list, there is a calm and curious possibility. Maybe one day, somewhere down the long arc of human or post-human history, a future descendant of our species will assemble that list. Not in our lifetimes. Probably not for many lifetimes, but in some distant century, when our names are no longer remembered and our technology looks primitive compared to whatever is current then, a project may launch. A probe may depart. It may cross trillions of kilometers in the dark, and after centuries of silence, a faint signal may return, carrying data from another star. If that happens, we will not be there to see it. But our role will have been to be the species that first looked up at the night sky and started doing the math. To be the ones who first calculated how vast the gap was. To be the generation that first felt the full weight of the light year as a real number. The first interstellar probe, if it is ever built, will be built by people standing on a foundation that we are constructing now. Every observatory, every textbook, every long thought about the cosmos that anyone has ever had. All of it is part of the slow accumulation of attention that might, one day, reach across the gap. Tonight, though, we are still on the near side, looking out, wondering. And the wondering is part of what we are. Our species, for all its limitations, has been doing this for a very long time. The earliest stargazers carved star charts into stones before they had written language. The earliest astronomers tracked the movements of planets and built calendars and predicted eclipses. The earliest philosophers asked what the stars were made of and whether other worlds existed beneath those distant points of light. They did not know how far away the stars actually were. They did not know that a light year was an idea, let alone what one looked like. But they were looking. The looking is the beginning of everything that came later. Now we know the distance, we know the timescales, we know the energy costs, we know how impossibly hard the crossing is. And we are still looking. The looking has not stopped. The terror of 1 light year does not make us close our eyes. If anything, it makes us look harder. To press for more sensitive instruments, to squeeze more detail from the photons that do reach us, to imagine, even when imagination outruns physics, what it might be like to actually go. Maybe that is the deepest part of this. Maybe the human relationship with 1 light year is not really about transit. Maybe it is about acknowledgement. A light year is the universe's way of telling us that we are small, that our reach has limits, that the scale of reality is not arranged for our convenience. And our response, generation after generation, has been to bow to that fact and then keep looking anyway. Not to insist that we must conquer it. Not to pretend it does not matter. Just to keep looking. To keep asking. To keep building telescopes and theories and dreams. There is a quiet dignity in that. A species that has accepted the terrifying scale of the cosmos and decided, all the same, to study it. To map it. To learn its history. To understand its forces. Not because we can ever physically possess it, but because comprehension is its own form of contact. The light year, in this sense, is not just a wall. It is a teacher. It shows us what we are by showing us what we cannot easily do. It defines our limitations and, in defining them, makes possible everything we have built within them. Every triumph of human astronomy has happened on the near side of 1 light year. We have never crossed it. We have never had to, in order to learn what we have learned. The cosmos has been generous enough to send its data toward us, and we have been clever enough to read it. So when you next stand under a clear night sky and pick out a bright star, take a moment to do the small calculation. That star is somewhere between 4 and many thousands of light years away. The light reaching your eyes left it sometime between 4 years ago and many thousands of years ago. It has been crossing the void at 300,000 kilometers per second for all of that time, without rest, without slowing, without faltering. It has crossed the very distance we have spent this evening calling terrifying. It is finishing its journey in you. Now imagine, just for a moment, what would happen if you tried to send a single photon back? You point a small laser at that star and pulse it. The light leaves your hand, climbs out of the atmosphere, escapes Earth's gravitational well, and begins its own journey across the same void. If anyone is watching at that star, they will not see your signal for years, decades, possibly never, if the star is too far and your laser too weak. The reply, if any, will not come for at least the same amount of time again. The exchange, by the time it could complete, would have outlasted your life. Your civilization might not be around to see the answer. This is the daily geometry of the cosmos. We receive light constantly. We can in principle send light, but the timescales make any conversation effectively impossible, and the matter we are made of cannot make the crossing at all. Not in our bodies. Not in any way we recognize as travel. Not within the patience of our species so far. It is enough to make a person feel deeply alone. And in a real sense, we are alone. Not necessarily because no one else is out there. We do not know whether others exist, but because the universe has set up its laws to keep everyone alone in the sense that matters most. Each civilization, wherever it arises, sits in its own gravity well, surrounded by trillions of kilometers of insulating dark. Each one looks up and sees the same kind of sky we see. Each one calculates the same distances. Each one understands the same impossibility. And each one is, in the most literal sense, isolated from every other. But there is one thing that binds us across the gap, and that is the light. The same photons that carry information to us also carry information to them, if they exist. Every star in the galaxy is broadcasting its presence in all directions at the speed of light. Every supernova explosion, every galactic merger, every gravitational wave, the universe is full of signals, and those signals reach every observer who can detect them. We do not have to share space to share data. The light belongs to everyone who can see. So in the end, the terrifying reality of crossing 1 light-year is also, in some twisted way, a comforting reality. The universe is too big to cross, but it is not too big to know. Knowledge crosses easily. Photons do the work for us. We sit still, we open our eyes, we build our instruments, and the cosmos delivers itself to us. We will probably never set foot on another star's planet. We will probably never even send anything within 1,000 kilometers of the surface of Proxima Centauri b. We will probably remain, for the foreseeable future and possibly for the entire duration of our species, a civilization confined to a single solar system, possibly a single planet, possibly only the warm, narrow shell of biosphere where our particular kind of matter can survive. But within those limits, we have already accomplished something the universe seems designed to prevent. We have understood it. We have built a mental model of the cosmos that matches reality to within tiny margins. We have placed ourselves in our minds at the correct location and the correct scale. We know what we are and where we are and how vast the rest of it is. That is not nothing. That is, in a real sense, everything. The light year stays terrifying. The kilometers do not change. The energy curves do not soften. The timescales remain inhuman. And yet here we are, on a small wet planet, talking about it, thinking about it, building a shared cultural understanding of what it is and what it means. The fact that this is possible is itself a small miracle. The fact that a species evolved to chase prey across grasslands can now contemplate the distance light travels in a year is one of the most surprising outcomes the universe has produced. We did not need to be able to do this in order to survive. Survival did not require us to know how far away other stars are. But we know anyway. We figured it out. And we keep figuring out more, so the question that started this journey, whether we can cross 1 light-year, has an honest answer. The answer is probably not in any way that would let one of us walk back from the trip. Not with our bodies. Not in our lifetimes. Not with technology we currently possess or are likely to possess in any near future. The terrifying reality is that the universe has made the simplest interstellar unit functionally impassable for things like us. But the question that follows from it, whether the inability to cross diminishes us, has a more interesting answer. It does not. Because we are not, finally, the kind of creatures that prove our worth by traveling. We are the kind of creatures that prove our worth by understanding. And the understanding works. Across 1 light-year, across 100, across 1 billion. The light comes to us, we learn from it. We assemble the picture. And the picture becomes part of who we are. This is the strange, exhilarating truth of being a curious species in an enormous cosmos. We cannot go there. But we can know. And the knowing, alone, is enough to make existence feel larger than its tiny biological footprint. We have not crossed 1 light-year. But we have crossed something just as significant. We have crossed from a state of ignorance to a state of comprehension. We have crossed from believing the night sky to be a fixed dome of lights to understanding it as a vast three-dimensional structure of stars and galaxies and voids. We have crossed from thinking ourselves to be the center of the universe to recognizing ourselves as inhabitants of a single ordinary planet orbiting a single ordinary star in a single arm of a single galaxy among trillions. That crossing, the crossing of understanding, has been the great journey of our species. It is the only interstellar voyage we have ever truly made, and it is, in its own way, magnificent. The light year remains, the cold remains, the distance remains. The terror, if you choose to feel it, remains. But so does the looking. So does the wondering. So does the patient accumulation of knowledge by a species that refuses, despite every reason to give up, to stop paying attention. Tonight, somewhere in the dark above your roof, light from a star 1 light-year away is finishing its journey. It has crossed trillions of kilometers to arrive at the moment it meets your eye. It will not visit again. The next photon will be a different one, freshly arrived from the same source, also having completed the same enormous trip. Every star you can see is doing this constantly, sending photons across the void in every direction, including yours. The universe is reaching for you. It is reaching for everyone who looks up, and it has been doing so for the entire history of life on this planet, whether anyone was watching or not. Now, for the first time in the history of our species, we know what is happening. We know what the light is. We know where it comes from. We know what 1 light-year means. We carry that knowledge in our heads when we step outside at night. And the simple act of standing under the sky becomes, in light of that knowledge, an act of cosmic participation. Not by traveling, by receiving, by understanding what we are receiving, by being the small, awake thing at the end of a very long road. If you have stayed with us through this entire journey at Hidden Beyond Stars, thank you. These long, quiet explorations into the structure of the cosmos are made possible by listeners willing to sit with the size of the universe and not look away. Please take a moment to like this video and subscribe if you have not already. In the comments, tell us what crossing a light year would mean to you. Would you send a probe? Would you board a generation ship if it were ever offered? Or would you stay behind and watch the data come home? There is no wrong answer. Every answer is a window into how we relate to the immense space around us. For now, the only crossing we have is the one made by light. The only reach we have is the reach of our attention. The only voyage we have completed is the voyage from ignorance to understanding. It is a smaller voyage, perhaps, than the ones the dreamers wanted. But it is real, and it is ours. And it has carried us across more than any spacecraft ever will. 1 light-year remains between us and the next thing. Trillions of kilometers of dark. Thousands of years of journey at our fastest speeds. Energy budgets we cannot meet. Time dilation traps we cannot escape. Dust grains that would erase us at relativistic velocities. The wall stands. The wall is not coming down soon. But the light keeps arriving. And as long as it does, we are not entirely cut off. We are listening, we are reading. We are watching the cosmos deliver itself to our doorstep in continuous quiet streams of photons that have crossed everything we cannot. We are the small, still creatures at the receiving end of an infinite correspondence. And the correspondence is enough, for now, to keep us looking up. The night sky waits. It always has. The light is on its way. It always is. And 1 light year, terrifying as it is just the first of the distances we have learned to live with. The first wall in a universe of walls. The first reminder that we are small. The first lesson in how to be small with grace. Sleep well under that sky tonight. The photons are still arriving. The universe is still riding. And for as long as our species lasts, someone will still be reading. There is one more place to stand before we close this exploration, and it is the strangest place of all. It is the imaginary midpoint of a 1 light-year journey, half a light-year out. The exact halfway mark between our sun and the symbolic boundary we have spent this evening trying to reach. Imagine being there. Imagine, somehow, a spacecraft drifting through that point in deep interstellar space, half a light-year from anything. The sun is behind you. A faint, bright dot, not particularly distinguishable from the field of stars surrounding it. The destination, if you have one, is ahead. Equally distant, equally indistinguishable from the rest of the cosmos. In every direction, the sky looks essentially the same. Stars in their patterns. A slight band of brightness from the Milky Way's disk. Darkness in between. There is no near object. There is no landmark. There is no current. There is no breeze. There is no orientation except the one you carry with you, the memory of where you came from, and the calculation of where you are going. This is the loneliest place a human-built object can occupy, and no human-built object has ever been there. Voyager 1 is the closest, and Voyager 1 is still inside the Sun's gravitational basin. It is still, in a real sense, at home. The actual midpoint of a 1 light-year voyage is somewhere none of our machines have ever reached, somewhere none of our minds have ever been, except in thought experiments like the one we are conducting now. And at that point, if you turned around and looked back at the Sun, you would see something profoundly humbling. Our star, the one that warms our planet, the one whose energy underpins every breath we take, would appear as a faint pinprick. Not the dominant feature of the sky. Not the obvious center of anything, just one star among many. Slightly brighter than its neighbors, because it is closer, but only slightly. The casual observer would have no reason to single it out. There is nothing about the Sun, viewed from half a light year away, that announces itself as special. It is one yellow dwarf in a galaxy of 200 billion stars, and from that vantage point, it looks like exactly that. This is what our home looks like from the threshold we cannot cross. A dot, a point of light, barely distinguishable from any other. Everything we have ever known, every kingdom, every war, every love story, every scientific discovery, every grain of sand, on every beach, contained inside a pinpoint that an observer at the halfway mark of 1 light-year would have to squint to find. And that observer would not be far from us. They would be inside the Sun's gravitational influence still. They would be, by any galactic measure, in the immediate neighborhood. And yet, our star from there is already small. Now extend this picture. Go to 1 light-year out, the Sun shrinks further. Go to 10 light-years out. The Sun is barely visible to the unaided eye. Go to 100 light-years out, and our star vanishes into the background entirely. There is no way to find it without instruments. It is no longer one of the brighter stars in the sky. It is just one of the countless faint specks that make up the background light of the galaxy. The civilization that lives around it, our civilization, is so small that no observer from 100 light-years away could possibly detect that we exist, no matter how powerful their telescope. We do not register at that distance. We are not a feature of the cosmos. We are an unremarked particle within it. That is the truth that 1 light-year teaches when you really sit with it. Not just that we cannot cross, but that we do not, in a galactic sense, occupy meaningful space. Our entire range of presence, including every radio signal we have ever broadcast, including every photon we have ever sent outward in any deliberate way, fits inside a bubble that is, on the scale of the galaxy, almost invisible. Even a creature standing at the halfway mark of 1 light-year, just half the distance we have spent these hours describing, would have to know where to look to find us. And they would have to look very carefully. And yet, paradoxically, we are not nothing. We exist, we think, we feel, we build, we learn. The fact that we are unobservable from 100 light-years away does not make us unreal. We are real. We are simply small. And small is not the same as meaningless. Small things can hold within themselves entire universes of experience. A single human life, contained inside a body that is itself a tiny speck on a tiny planet, contains memories and relationships and ideas and emotions that, viewed from the inside, feel infinite. The smallness is a fact about scale. It is not a fact about value. This is, I think, the final lesson that 1 light-year offers. The terror of the distance is real. The impossibility of the crossing is real. The cold, the energy, the time, all of it is real. But the response to these facts does not have to be despair. It can be something else. It can be a deepened appreciation for what we are. A species that fits inside an invisible bubble in a galactic ocean and still manages, against all odds, to know that the ocean exists, to map it, to love what it contains, to pass that love down through generations who will never personally cross any of the distances they have measured. There is something almost stubborn about that. Stubborn in the best sense. The universe set the rules. The rules say we cannot cross even 1 light-year, not really, not the way we would want to, and we said fine. We will look anyway. We will understand anyway. We will pour our attention into this immense space, and we will refuse to let its size diminish our effort to comprehend it. That stubbornness, that quiet refusal, is one of the most beautiful things our species has ever done, so perhaps this is where we leave it for tonight. With the recognition that 1 light year, terrifying as it is not an enemy, it is a teacher. It is the universe's gentle but unyielding reminder that we are guests in a structure far larger than our bodies. It is the wall that defines our cradle. And the cradle, viewed from inside, is not a prison. It is a vantage point. It is the place from which we have learned everything we know about the rest of the cosmos. The night sky will be there tomorrow. The same stars will be visible from your part of the world that have been visible for thousands of generations. The photons will still arrive. The light from 1 light year away will still complete its journey in the small theater of your eye. And you will know, in a way that previous generations could not have known, exactly what that means. You will know how far the light traveled. You will know how long it took. You will know that the journey it just completed is one our entire civilization has never managed and may never manage. You will know that despite everything we cannot do, the universe is still touching us, continuously, in quiet floods, forever. That is the gift of having been born into a moment when the cosmos is still observable, when our instruments can still read it, when our minds can still hold the picture. We are early in cosmic history. There will come a time, many billions of years from now, when most of the universe will have receded beyond detection, when even the cosmic microwave background will have stretched into undetectable wavelengths, when future civilizations, if any, will have no way of knowing that anything ever existed beyond their local cluster. They will live in a smaller, lonelier universe than ours. We are not in that universe, we are in this one. The one where the light still arrives. The one where the data still flows. The one where 1 light year, while uncrossable, is at least measurable. And measurable is enough. Measurable means we can know it. We can study it. We can sit beneath the night sky and feel the strange comfort of comprehension. The strange comfort of being a small thing that has learned the shape of something enormous. Maybe one day in some far century, a descendant of ours will look at the data returned by the first interstellar probe and feel something we cannot quite feel now. The satisfaction of having reached, even slightly, even with the cold instruments of an unmanned machine. Maybe one day that probe will have made its lonely journey across the distance we have called terrifying, and it will have arrived, and it will have spoken back through a faint signal, and the people who receive that signal will know that the wall, while still standing, has been touched. But that is a future we will not see. For now, we have only this: the light arriving, the questions persisting, the species, small and stubborn, still looking up, still asking, still building the patient instruments that turn unreachable distances into knowable distances, still doing the only kind of cosmic travel we are equipped to do, which is the travel of understanding. 1 light year, the first wall, the smallest piece of the impossible, the unit of separation that defines the architecture of our cosmic isolation, and the unit also of our cosmic education. The thing we cannot cross has taught us almost everything we know about everything else. So when you next find yourself outside on a clear night, away from the lights of the city, with the cold air sharpening every star to a fine, bright point, take a slow breath. Look up. Pick a star. Any star. Remember that the photons entering your eye in that moment have completed a journey across at least 1 light year, often many more. Remember that those photons are real, that they crossed a void you cannot cross, that they arrived on time, that they brought information from a place no one you will ever meet has ever been. Remember that you are receiving a message older than your own existence. And remember that you, against every reasonable expectation, are equipped to understand what that message means. That is what the night sky is. That is what 1 light year really is. Not just a wall, not just a distance, a relationship. The terms by which the universe and a small awake species on a small wet planet have agreed to know one another. The universe sends light. We receive it. The conversation is uneven, but it is real. And as long as there are eyes to look and minds to wonder, the conversation continues. The cold is real. The dark is real. The terror is real. But the looking is real too. And so, for now, is the small, persistent wonder of those who, knowing exactly how far away everything is, refuse to stop paying attention. If you have walked this entire journey with us tonight at Hidden Beyond Stars, thank you. These quiet, long explorations are made possible by the people who care enough about the cosmos to sit with its scale. Like the video, subscribe to the channel, and tell us in the comments what you would want to see beyond 1 light year if you could see anything at all. The universe is still talking. We are still listening. And there is always another distance to consider. Until the next journey, look up gently. The light is on its way. It has been on its way for a long time. And it will arrive tonight, whether anyone is watching or not.